All right. Okay, so we're going to continue talking about tolerances today, and we're going to focus on metric for this lecture on metric tolerances, which are a little bit different than the English tolerances that we already did. Okay, so let's see, limits and basic size. We already know about that. We know about tolerancing and MMC, which is most material condition, and least material condition is LMC. Okay, so you've already seen that, and they have the same definitions in the metric part of this as it does in the non-metric part, the English part. Okay, so let's go through some definitions here. If you see this sketch here, right, we've got a shaft and a hole just like before, except now we've got millimeter definitions or limits. Okay, so the limits for the shaft is 2.1 to 2.2, right? The basic size, anybody want to venture to guess what the basic size is in the chat box? 2. Yep. Good job. And then what else do we have? We have the tolerance. So the tolerance is what? Do you remember how to do the tolerance for the shaft? Anybody want to throw a number out? 0.1. Yeah, it's the range, right? So it's the biggest minus the smallest. Okay, and you can also figure it out for the limits for the hole and for the hole tolerance as well. It's just the range. Okay, so that was a review, and there are the answers. Okay, so I think you guys got this down. This should be review, but now we've got this new definition, right? This is called the upper deviation. Okay, so that's kind of a weird way to think about it, but it'll make sense when we talk about applying it to various cases. So the upper deviation is basically just the basic size and the maximum deviation allowed. Okay, so the maximum limit allowed, and you take the absolute value of that. So it's always a positive number. Okay, so maybe an example would be good. So what's the upper deviation for the shaft here? Anybody want to guess? Somebody said 0.2. Good. Okay, and then there's a lower deviation. The lower deviation is the difference between the basic size and the minimum permitted size of the part. Okay. So let's do an example again for the shaft. So what's the lower deviation? Anyone can put it in the chat box. .1. Okay, very good. And then there's the fundamental deviation. Okay, that's the deviation. The fundamental deviation is the closest deviation to the basic size. So the fundamental deviation is the smaller of the upper deviation and the lower deviation. Okay, a letter in the fit specification represents the fundamental deviation. Okay, so let's go ahead and take a look at this. So we have a shaft and hole system. So see if you can write it down on a piece of paper or think about it, right? And what the upper deviation, lower deviation, and fundamental deviation would be for the case shown here. And I'll give you a little bit of time to do that. You don't have to put it in the chat box because there's 6 numbers, so. Uh-oh, we may have just let someone in I don't want in here. Okay, let's go to the next page. Okay, I hope that's all what you guys got. It's a good example to keep handy if and when we post the test for this this chapter, which will probably be next week sometime. Okay, so now we're going to go back to in memory lane. And we had talked about clearance fits, interference fits, transition fits, and line fits. Okay, so a clearance fit, there's always a space between the hole and the shaft. An interference fit means that there's never a space. Transition, it depends. You can have a space or no space. And a line fit is there's a space or contact. Okay, so let's take a look. And then this is the definition with respect to the numbers. So minimum clearance is always greater than 0. The interference, the maximum clearance is always less than or equal to 0. With the transition fit, the maximum clearance is greater than 0. And the minimum clearance is less than 0. And then there's the line fit. Okay, so this should be more or less a review for everyone. Okay, so anybody want to venture what type of fit this is? Interference. Good job. All right, now we got some definitions, and these are the kind of things you want to, keep to the side when you're doing your homework or doing your at-home exam later on. So there's what's called an International Tolerance Grade number, an IT number. Okay, the IT numbers are a set of tolerances that vary according to the basic size and provide the same relative level of accuracy within a given grade. So those big red arrows are pointing to the IT numbers, okay? The important thing to notice is that the smaller that number is, okay, it provides a smaller tolerance. So the bigger the number, the looser the fit, okay? Then there's the fundamental deviation, which when taken in combination with the IT number, defines the tolerance zone. Okay, so now the arrows are pointing to the fundamental deviation. So the tolerance zone would be H11, okay, for the hole, and C11 for the shaft. So the capital letters are for holes and the small letters are for shafts. Okay. All right. And there's, of course, a standard associated with it. Okay. So you can look up those standards. They have a new version, a revision from 2004. They probably have another one more recent. Okay, but they don't change much from year to year. So remember, the higher the number, the looser the fit. Okay, so here are some examples with the corresponding fits. So you can see when the number is high, it has a very loose fit. So this is loose running right here. Okay. And then here the numbers are very small, and those are force fits. You actually have to hammer in the shaft into the hole. And you might want to do that if you're connecting two parts and you don't want them to come apart, right? Some furniture, might be like that. You could get the different parts, put the dowel in, you have to hit the dowel in one end and then hit that with the other part, and it's a force fit. So it never comes apart once you put it together. Okay, so you might want, really low IT numbers, which tells you how tight of a fit it is. Also, you don't want things too loose. If you have like a shaft in a hole and it's got to rotate, you don't want it to wobble. Okay, so you might pick one of the close running fits, for example, or free running fits, one of these. Okay, and you can see the hole in the shaft can have different numbers. All right, so the difference between the hole and shaft basis fits is going to be discussed. All right, so here we go. Here's another example. So the fits are specified by the fundamental deviation, which is the letter, the IT number, which is the number. So H is the fundamental deviation for the hole, and 11 is the fundamental, or is the IT number for both the hole and the shaft in this case. So the red circle corresponds to the hole, which is the uppercase, and the shaft is circled with green, and that's the lowercase. Okay, so you have the fundamental deviation of the shaft is the little c, and the IT number for the shaft is 11. Okay, and from those numbers, the machinist can actually make the part and know what the tolerances are. All right, let's see how we can do here. So let's take a look at this, and you can write this down on a piece of paper. You don't have to put it into the chat box. So the first question here with the question mark is pointing to this first part here, which includes a diameter symbol and the 50. So, take a look at the choices you have in the box. Okay. And try to think of what the answer is. Okay. Then we'll move to the next one. So write it down on a piece of paper, and we'll give you the answers in a few more slides, just like we would in class with iClickers. And then you can check yourself and try to figure out how good you are based on the previous slides, okay? All right, now what about this one? So it's pointing just to the H. What is that telling you? Is that the fundamental deviation, the hole tolerance zone, the basic size, the shaft tolerance zone, or the IT number? Let's see if you can write that down. Okay, and then we'll move to the next one. The 8, what does that represent? Which of these 5 answers? And then H8, right? Both of them together. What does that represent? And then F7, what does that represent? Okay, now let's go look at the answers. So this is pointing to the basic size, right? It's the basic diameter is 50 millimeters. Okay, because remember, we're metric now. Okay, so the second one is the hole tolerance zone, right? We know it's the hole because it's a capital letter. Okay, and both of them together gives you the zone that you're in, the tolerance zone that you're in. This next one here is the shaft tolerance zone, same thing, and you know it's the shaft because it's a smaller case letter. Okay? Now if we break it apart and look at the individual within a tolerance zone, the first letter, the letter here, is the fundamental deviation, and the number is the IT number. Okay, now what does this mean? Well, this will become a little more clear when we move into looking these tolerances up on a table. So if you're given this as a specification, right, as a tolerance for a certain part in your design, okay, you can look it up on the table and know how to machine it. Okay, so basic hole system. So, you know, you're going to have a basic hole system or it's going to be a basic shaft system. The reason it's either or, it's what's more important. Okay, so if you use the basic hole system, you want the basic size to be attached to the hole dimension. Okay, and that would be, for example, if you want to tolerance a shaft based on the hole produced. Okay, so I'm going to produce a hole because I've got a certain tool that'll make that hole a certain size, and then I want to buy a shaft from McMaster-Carr or someplace online that'll fit that. Okay, so I'm going to use a basic hole system because my drill or my reamer or my broach is going to define that hole. And then I want something to fit to that. And then the shaft system is I have a shaft and I'm going to connect it to something. You know, how do I make the hole? So the shaft is actually driving, you know, how I'm going to make the hole. So that would be a basic shaft system. Okay. So here we go. We have a case here where we have a shaft and hole and we're given the tolerances. So we know what the tolerances are. And for the box that's colored in, okay, what kind of system? So that's the third row there. Is that a shaft system or a hole system? What do you think? Right? You can write it down on your piece of paper if you want to, or someone wants to jump in and just throw it up in the chat box. Feel free to do that. Just one person. Take a stab at it. You're not graded on this. B. So B is a shaft. Yeah, because it's a shaft system because it's connected. You can see the basic size is within the shaft tolerances. Okay, so you can kind of guess by looking at the range. Okay, what about this one? A or B, hole or shaft? Yeah, it's a hole system. The basic size is attached to the hole. Okay, so you can see how that kind of works. And then the types of fits takes a little doing. You have to look at the definitions. It's kind of hard to remember all of them. But you can kind of look at it. Clearance, right? That's pretty obvious because the shaft is always smaller than the hole, right? So that's a clearance fit. You always have a space. Interference, right? Look at this one. The biggest the hole can be is still smaller than the smallest shaft. So it's always going to interfere. Okay. So there is no space. So it's interference. You got to hammer that shaft into the hole. And transition is you've got some overlap. Okay. So if the shaft is 60.002, for example, and the hole is 60.030, the shaft's going to be smaller than the hole, but there's also a case where it can be bigger than the hole. So that's called a transition fit. Okay. All right. So this isn't too bad, but you know, you're going to have to refer back to it. And if you work in an engineering company where you deal with this kind of tolerancing all the time, you'll learn it really well. Now at least you know that there's a difference and it means something and you can go look it up. Okay. So let's look at an example. All right. This is the example here. We've got a diameter of 30, so the basic size is 30. We got a hole with an IT number of 11, and then we've got a fundamental deviation that's H, right? Let's find out what that means in a minute. And then the same thing for the shaft. We've got a fundamental deviation of C with an IT number of 11. And this creates a certain type of fit. So let's take a look at what the tolerances would look like. So you can look up these things in tables. The book comes with some tables. I provide some tables with the homework because sometimes the range in the homework problem is outside of the tables that are given in the book. So make sure you look at those attachments to your homework assignment. Okay, so here we can see fundamental, or the basic size, excuse me, is a diameter of 30. So we look at the basic size column, which is the first column in this table, and we look for 30, and there it is. It's right at the bottom. Okay, so now we're going to say, okay, that's cool. Now we want to know H11. So we find H11, which is for the hole. Because it's a capital letter, we know it's for the hole. Okay, and we go look down to where it crosses with the 30, and this gives us our tolerances for making the hole. So now I know how to machine my hole. It's got to be between 30.000 and 30.130. Okay, so then we know that the two are connected through that table, right? So we can go look it up for loose running, but it's only loose running if we do it in combination with the shaft, right? So the shaft is C11, so we go down here and then we find the range. Okay, and then that's a loose running fit. So if you're an engineer wanting to design something with a loose running fit, you go look at the table and then you can find the corresponding numbers, and that's close to your basic size, and then you can just define it that way, and your machinists and your manufacturing people will know how to make that. Okay, so that's why we have specs and tables. It makes things easier, or it's supposed to. And of course, if it was a free running thing, then you would specify it as an H9D9, right? It's a smaller number. So a smaller number means that the fits get closer together and you have less space between the shaft. Okay. All right, let's go to the next one. So here again, we have the same example, and we're going to take a look at what the tolerance is and what type of system it is and the fit. So the system, okay, since we know the limits, would that be a hole system or a shaft system? Right, remember it applies to both. All right, we'll get to it. Tolerance, right, that's the range. Remember, the upper minus the lower limit. The difference between the two gives you the tolerance. So in this case, for the hole in the shaft, the tolerance happens to be the same. Okay, the system is a hole. Why? Because the basic size, right, this is the basic size, diameter here, is associated with the hole. Okay, and what kind of fit is it? It's a clearance loose running fit. Okay, so that means it has a lot of space in it. And we just looked at the chart, and the two first columns were for loose running. So basically what that means, there's always a space, right? The clearance is always bigger than zero. The clearance, again, is the difference between the hole and the shaft size for all the possibilities that you can make. Remember, everything is tolerance. So the shaft will have a range of diameters, and the hole will have a range of diameters, because nothing is ever perfect. All right. So here's another example. Basic size again is 30 millimeters, but we have a different IT numbers for the hole, capital letter, right, and the shaft, smaller case letter. So let's take a look at that. So we go look up that table, that page in your book, and you find the basic size again, and now you're looking for P7 and H6. You find that. Oh, we know it's a locational interference, and then we know how to make it. And if you look at it, okay, the shaft, right, the biggest the shaft can be okay, is just slightly smaller than the smallest the hole can be. So that's called a locational interference. Okay, and you remember that the shaft isn't going to be perfect all the way down. It's going to have some variation in diameter too, depending on how good your machining is. Okay, but anywhere you measure along the shaft should be within tolerance. All right, so let's take a look at that. The tolerance again is the range. Okay, and the system, well, the basic size is associated with the shaft. Oops. Okay, and the fit is locational interference. That's what's on top. Okay, so you can use these tables to answer the questions in the homework, and you'll be doing a lot of that, and you'll also be answering questions on the exam. Okay. All right, so selecting tolerances. Okay, always remember that when you make things higher toleranced, right, it's harder to make and it costs more money. So as an engineer and a designer, you want to try to keep the tolerances as loose as you can and still have the part function as intended. Okay. And the tolerances always depend on factors like how long is the engagement. If your shaft is moving through a very deep hole and you have a long shaft, then you probably want a looser tolerance because you've got to maintain the tolerance all the way down the hole and all the way down the shaft. And then what kind of load are you going to have on it? So how much slop is it that you want to have with that? Now you can do a lot of cool things by lubricating the shaft and hole system to reduce the slop, right? And while maintaining some kind of a fit that you can still slide. Okay. And then the speed, right? How fast is the shaft going to go in, or how fast is it going to rotate within the hole? The temperature, right? Think about it. If the temperature decreases, the shaft gets smaller, but so does the hole. Okay? Or does it? No, the hole gets bigger. That's right. So the shaft will shrink, the material that the hole is in will also shrink. Okay, and then if the temperature goes up, the opposite happens. The shaft gets bigger, the hole gets smaller, I think. Let's think about that. Yeah, the hole gets smaller. Temperature goes down, the hole gets bigger, the shaft gets smaller. So you can see that it depends on what temperature you're going to run your part at. That'll determine or be a determining factor as well on how you're going to tolerance something. So, at first this looks pretty straightforward, but the temperatures become real important, especially if you're like designing an engine or, a jet engine or something like that, or a spacecraft, right? They go to extreme temperatures, very cold, very hot. And so you want your part to work in all possible temperature ranges, okay? And then you will gain experience. Oh, someone just put down like the SR-71 Blackbird. It had a lot of loose tolerances. Yeah, it did. It did. And, pressure can play a role too, right? You're designing a submarine, that might be important. So this shows you how you would machine different IT grades, right? The IT number. Remember, the bigger the number, the looser it is, and the cheaper it'll cost. And if you look at this, this table, right, all the way at the bottom is die casting. That's the sloppiest tolerancing you may have, right? That's where you make a mold of something, usually with sand. You can do sand casting. There's also other kinds of plastic casting and whatnot, but sand is typically done, and then you pour molten metal into the mold, and then you end up with a part. once it cools down. That's going to be real rough, the tolerancing for it. And then all the way at the top is lapping and honing. That's when you polish something to a very fine tolerance. So like you're making a mirror or you're making a lens for a telescope, something like that. That's where you would lap and hone things. Okay, and then you got everything in between. So turning is the turning of the part on a lathe. Boring is drilling a hole in it. Milling is taking it off, taking material off with a mill. Okay. And you have a whole variety of different machining operations. And generally speaking, as you go from the bottom up, it gets more expensive and takes more time. All right, so you can get what's called tolerance accumulation. I think we talked about that in dimensioning, right? We talked about how do you dimension something to fabricate a part, and how does the tolerancing accumulate depending on how you dimension it, right? What's important. So this should be a review. The tolerance between two features of a part depends on the number of controlling dimensions. So we have a number of controlling dimensions here. So if you look at the difference, if you were to measure between A and B, right? What's the range of that dimension going to be? Well, if you go 20 plus 30 plus 20, you're going to get 70. So on average, the distance between A and B is going to be 70. But now you've got this first part's going to be able to vary by 0.1. The second varies by 0.1, and this third varies by 0.1. So you're going to accumulate all of those tolerances, okay? So think about this, you know, if you have more of these types of dimensions between A and B, are you going to have more tolerance accumulation or less? Right? Okay, you're going to have more because the two features, the maximum variation between the two features is the sum of the tolerances on the controlling dimensions. So that's how the machinist sets it up and does it based on what you do in your design, how you define it. So you may have a reason to make this 20 plus or minus 1.1 and this 30 plus or minus 0.1 and this 20 plus or minus 0.1. That might be very important for you as a designer. It could be you have a belt that runs on these different shafts or these different diameters of the shaft, right? So you really want that width to be well controlled, okay? But then the distance between A and B is going to vary more, but you may not care, right? It may not make a difference. Okay, so that then you would have a reason to do it that way. But let's say the distance between A and B is real important, right? How do you get rid of this? Well, there's a couple of different ways we can do that. Okay, so let's take a look at this example again. And if we wanted to look at the tolerance accumulation between A and B, that would be 70, right? Plus or minus something. So can someone put in the chat box what that plus or minus would be in this scenario? Again, that's the distance between A and B is 70 plus or minus something. We got a plus or minus 0.4, 0.3, 0.3, 0.3. Okay. So it's 0.3. Okay. Because if you look at the possibilities, okay, this would be perfect, right? This measures at 20, this measures at 30, this measures at 20. So it's perfect, okay? So this distance between A and B in this case would be 70. Okay, now here's the worst case. Each one of those parts or those components are all big by 0.1. It's still within tolerance. We haven't broken any tolerance rules. It's still gonna pass inspection. It's not gonna get thrown away. So you have 20.1, 30.1, 20.1. So that's on the big side. Okay, so the difference between A and B is going to be 70.3 in the worst case. Okay, and then you also have the minimum worst case. That was the maximum worst case. This is the minimum. So everything's a little bit smaller by 0.1, right? Remember, each one of these parts is plus or minus 0.1. So now everything's too small, or not too small, but as small as they're allowed to be. And then you add that up, that's 69.7. Now you know what your tolerance is between A and B. It can be 69.7 all the way up to 70.3, which is a plus or minus 0.3, which is what you guys said, okay? So for those of you who didn't quite get it before, hopefully that helped you figure it out. Now here's another interesting case, okay? Again, we're looking at the distance and the tolerance between A and B, right? So we're going to measure between A and B. Okay, so what do you think the accumulated tolerance would be in this scenario? So you dimensioned it this way instead of the other way, right? Okay, we got 0.02. Is it 0.2? Or is it 0.2? Oops, good job. So let's see if that's true, if it is 0.2. It is, because this can vary plus or minus 0.1, and this can vary plus or minus 0.1. So you're the best, or the worst maximum case would be they're both a little bit long, or one's short and one's long, so the difference is 0.2 in length. And then the other case would be you have 40.1 and 109.9, and that would be when they're closest together. Okay, and that's again on the negative side of the base size of 70 by 0.2. Okay, so think about it a little bit if you don't quite see it. Okay, I'm going to post these updated notes soon. I might have already, but I'm going to check after class. All right, so again, let's go through the different scenarios. This is if it's perfect, right? You measure 40 for this one, and you measure 110 for this one. That means the distance between A and B is exactly 70. And then here is the minimum worst case. Okay, so the bottom one, or the one to the left, is a little bit big as it can get before you throw it away. And then the longest part is as short as it can get before you throw it away. And so that gives you 69.8. Okay. So that's what you get. Okay, and then here's another example of dimensioning it. So I'm dimensioning these three from this datum here, but then I'm dimensioning this one, okay, based on this feature. Okay, so what's the total tolerance accumulation in this case? Should be easy. 0.1, because that's what we're measuring when we're making it. Okay, so there you go. So if the accuracy of the distance between A and B is important, which dimensioning method should be used? Well, you're going to dimension that, right? If that's important, that's what you dimension. And you don't get any accumulation that way. All right, so now let's talk about formatting tolerances. We have several ways to do this. So if you remember, you can tolerance things from the biggest to the smallest with this diameter tolerancing here. So you've got the bigger diameter on top and the smaller on the bottom. Okay, and this could be for a hole, for example, right? Or you could dimension it this way. You can say the basis size is 20 millimeters, and it's a C11. So this is a hole because it's capitalized, and then this is your IT number. So if you go look this up, you'll get this range for the hole. Okay. Or you can dimension it this way, which means this. You can dimension it this way, which means that. Or you can just dimension it this way. All right. Remember, these are in parentheses because these are redundant dimensions to what's already there. So that was from the dimensioning chapter. If you put it in parentheses, that means it's there for clarity. Okay, and you might want to do that if your machinist is used to seeing this, or if he's used to using tables. Because if he's using tables, he might have certain combinations of tools to make that size you want based on these tables, right? So you can do both if you want to be really clear, but one of them's got to be in parentheses. Okay. You have unilateral tolerances, which means that, you know, you want a 40, and it can't get bigger than a 40, but it can get smaller. So that might be a shaft, right? To make sure it always fits in the hole. And then the hole has to be 40 or bigger. So this might be a unilateral tolerance for a hole. This might be a unilateral tolerance for a shaft. And then you know it's going to be a loose fit. Okay? So a single zero without a plus or minus sign, right? So that means it's going to be this size or bigger. And in the case on the left, it's going to be this size or smaller. Okay. Then you have bilateral. Okay, if you do bilateral plus or minus kind of thing, you always have to have the same number of decimal places. Okay. So both the plus and the minus have to have the same number of decimal places. If you write it like this, it's wrong. And so for the tests and for the homework, you got to make sure that you stay consistent. Okay, so you know, we had this one where this is the basis, and then you have a range around that basis. And then this one just shows you the range that are allowed. These are called limit dimensions. Okay, they also have to have the same number of decimal places. You can also do it this way, where you have a basis size plus or minus. Now this doesn't have to have the same number of decimal places as this, because what you're saying here, this is the base size is 45. And then this is the tolerance range around the 45. The 45 itself isn't one of the limits. Okay, so you wouldn't say 45.00, it doesn't make sense. Right? You're assuming that the base size is very tight, but it really isn't, because it's not being, the tolerance isn't being decided by the basis size, it's decided by the range around the basis size. So hopefully that makes some sense. Okay. So here's some more examples: unilateral and bilateral tolerances. Okay. So it's okay to put the multiple decimal places here. Limit dimensions, same thing, same number of decimal places. But basic dimensions with a tolerance, you don't do that. Okay. All right, angular tolerances, same kind of deal. They both have to have the same number of decimal places. So, you know, these are just some rules you have to adhere to when you're doing your drawings and your dimensioning. You know, if we would have had the project this semester, we'd be looking for that in your project designs. Okay, so we're almost done with this chapter. So here's a milling jack assembly example. So this might be something you would design, right, in the future. So you see the nice SolidWorks kind of design on the right. Okay, this is a milling jack assembly that you might build to help you machine parts better. Okay, so there's different ways that you can dimension this. So here we're saying the V anvil, right? This is this part up here, and there's a shaft. Fits into the sliding screw with an RC4 fit. Okay. So there's the hole. It's got to slide through there. This is a 0.375 inch, 3/8 inch. Okay, that's the basic size for the shaft and the hole. Okay, and then now we have to figure out what the limits are. So we go to our tables and we look it up. Okay, so here you see the shaft. It says down in the lower right here, it says RC4 fit, and it has a basis diameter of 0.375 inches. Okay, 3/4 of an inch. Okay, so what are the tolerancing for this? And then again, here you have a hole, same kind of thing, and a certain depth to it. Okay, so this depth goes down 2 inches. So this thing will fit into that. And this length here is also 2 inches. Okay, so you go look up on the table and you find that this is the hole size. So you better make sure your hole is within this range, this tolerance. And then this is the shaft, and it has to be within this tolerance. And if you look at this, the 3745, which is as big as that shaft can be, is always going to be smaller than the 3750, which is the smallest that the hole can be. And that's so this this V anvil can slide up and down, and then with a set screw, you can set it at a certain height. So you can fine adjust it, okay? And that's where you want it to be fairly loose, right? But not so it can, you know, the shaft can move around left and right, okay? So here's another example of parts fitting together. So where's that 0.65? Right here. Okay, RC5 fit. There's the hole. Okay, a set screw is going to go in here. And then this is the shaft that fits into it. Okay, on the left. The diameter is 0.625 or 5/8 of an inch, RC5. So now you look it up. If you're machining this for someone, you look it up and say, you know, what range can I have on this shaft, right? And what range can I have for this hole? So once you look it up, you can say, oh, okay, this is what my allowable range is. You can see, since it's a 5, it's pretty tight, right? And the hole is the same way. It's kind of tight as well. Okay, so that's a very tight tolerancing. All right. So here's another example with a drill jig assembly. So this might be something you would design and make to hold a part in a certain placement so that you can drill holes in that part very precisely and repeatably. So you might create a jig to speed up production. Let's say you've got to do 5,000 parts. So that would be a case where you would design a jig, and then, you know, that takes time in of itself. But once you have the jig set up, you can make this part quickly, right? Put the part in, drill a hole, put the part in, drill a hole once the jig is set up. Okay, so now we're going to take a look at this and say, okay, we want to calculate some of these tolerances. So here's one that says this hole has a diameter of 20 millimeters and a G7 H6. So that's the system, right? So G7 would be the hole dimensions, H6 would be the shaft dimensions. You look it up on the table, and you find out that this hole has a variation that's fairly tight as well. Okay. So you never want to over dimension. And we talked about that in the dimensioning part of the lectures, the last chapter. Okay, is anything over dimensioned? Right? Yeah, well, the diameter dimensions are correct. Okay, so is this over dimensioned? Let's take a look at it. Well, the dimension decimals don't match. The dimensions are inconsistent, so this range here is not consistent. Okay, with this range plus this range, right? So here we're saying plus or minus a different range than if you take a look at the variation allowed when you accumulate these two tolerances here. That's different than this tolerance there. So you pick one, right? Either you get rid of this one if this isn't important and you leave this one and this one, or you get rid of this one and leave this one and this one, or you leave these two and get rid of that one. Okay, so it's over dimensioned. Okay, and that's it for this chapter. So let me go